Hello, I am Mrinal Kanti Roy Choudhury. The title of this talk is An Introduction to Quantization for Probability Distributions. What is quantization? Quantization is a process of discretization. In other words, to represent a continuous or a large set of values by a set with a smaller number of values. It has broad application in signal processing and data compression. Now, what is the goal of quantization theory for probability distributions? Let P be a bold probability measure on RD equipped with a metric this, and let U be the largest open subset of RD for which probability of U equal to 0. Then the complement of U, which is this quantity, RD set minus U, is called the support of P and is denoted by support P. The goal of the quantization theory for probability distributions is to represent the support of P by a smaller or finite set of points in an optimal way. Now I give some example of support of P. When an unbiased die is thrown one time, then you can consider P as a bold probability measure on the real line with support of P, which contains 6 elements, and the probability of occurrence each of these 6 elements is 1 over 6. When an unbiased coin is tossed 2 times, then the associated probability is a bold probability measure on R square with support of P, which contains 4 elements. If one represents head and 2 represents tail, then head, 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 tail, tail, head, tail, tail. So here support of P contains 4 elements. In the previous case, support of P contains 6 elements. When P is a uniform distribution on the interval 0, 1, then you can consider P as a bold probability measure on R with support of P, which is the closed interval 0, 1, contains infinitely many elements. So in quantization theory, our goal is to represent the support of P by some finite number of elements. So how to do that? So here I give you an example. Suppose P is a bold probability measure on R and its support of P is P contains 6 elements, these 6 elements. And the probability of occurrence of each element is 1 over 6. And we would like to represent these 6 elements by a set alpha of 2 elements in R. And suppose the 2 elements are 2 and 5.5. Now, there will be some error, of course, because you are going to represent these 6 elements by 2 elements only. So the error is, if the error is calculated with respect to the expected squared Euclidean distance, then the error Vp alpha is given by, remember it is variance which occurs in statistics and probability. So the variance formula is this one. In the continuous case, this expression means this one. And in the case of discrete, we use this formula. So in this case, so if you use this formula, the error comes if you calculate. So x means x is element from the support of P. So 1, suppose x is 1, then you take which is the closest element in alpha, 2. So 1 minus 2 square 1 over 6. Then for 2, of course, 2. And for 3, the closest element is 2. So 3 minus 2 square 1 over 6. And for 4, it is 5.5. So this, like this way. And if you calculate, the error comes 19 over 24. Now suppose if you would like to represent these 6 elements by these 2 elements, 2 and 5, then if you calculate the error using the same formula, the error comes 2 over 3. For any other set beta of 2 elements in R, you can see this error, that means 2 over 3 is small, less than or equal to Vp beta. That is the set which contains 2 elements, 2, 5, gives the smallest distortion error. Such a set alpha, which is the set 2, 5, is called an optimal set of 2 means for P. and the corresponding error 2 over 3, which is the smallest error, is called the quantization error for 2 means and is denoted by V2P. So in quantization theory, our goal is to find these optimal sets for which the error is the smallest. Now, how it works? Suppose, so P is a Boyle probability measure on RD, and support of P contains elements in this region. And you would like to represent the support of P by, suppose, 3 elements by A1, A2, and A3. Once you have chosen these 3 elements, then you join these 2 elements, draw the perpendicular bisector, join these 2 elements, draw the perpendicular bisector, join these 2 elements, draw the perpendicular bisector. And you know these 3 perpendicular bisectors will meet at one point here. So if there is, so this region, in this region all elements are closest to A1, and this region is called the Warner region of A1. So if there is an element falls in this region, then we represent it by A1. If there is an element in this region which is called the Warner region of A2, and we denote it by capital A2, if any point falls in this region, we represent it by A2. Similarly for A3, if any point in the support of P falls on this boundary line, then we represent it by either A1 or by A2. There's an important property. If A1, A2, A3 is the optimal set of 3 means, then A1 must be the conditional expectation. See that A1 must be the conditional expectation in its own Warner region, which is this formula in the case of continuous case, and this is the formula in the case of discrete. Similar is the expression for A2 and A3. So what we understood from this slide, we understood that the elements in an optimal set must be the conditional expectations in its own Warner regions. But the converse is not true. Say, for example, same square, take the probability distribution as an uniform distribution. Divide this square by this diagonal into equal parts, here by this line. Now calculate the conditional expectations in this region and also the expectation in these regions. Here is A and B. Here is A and B. So here you have seen these 2 elements are conditional expectations. Here also conditional expectations. But in this picture, in this division, the error will be smallest. That means although in both the cases the elements are conditional expectations, these 2 representations actually gives the optimal set of 2 means. Here it is mentioned. If in both figures, the 2 points are the conditional expectations in their own Warner regions, but the second figure gives the optimal location of the 2 towers or 2 elements. So this shows the converse is not true. Next, now I am going to give you the general definition of quantization error. Let alpha is a subset of RD. So in the previous examples we have given for D equal to 1 and D equal to 2. Say B a finite set and R is a positive real number. So this R means we have taken, say in this example, 2. R is 2 in this case, in this example. So you can choose any R. Then the cost or distortion error of order R for P with respect to the set alpha is given by this same formula, same example. Now you are just generalizing it, taking any R. So this in the continuous case, as I mentioned before, this is the formula. Discrete case, this is the formula. Suppose alpha contains k elements, then this VRP alpha is same thing as this formula, where A1, A2, A3, AK are the Warner regions, the capital A1, capital A2, capital AK are the Warner regions of the elements A1, A2, AK respectively. So this is the error formula to calculate. Now, so of course, if you choose alpha, if you take different alpha, error may be different. The nth quantization error is defined by this formula. Quantization error means smallest error. So you calculate all kinds of error like this. And the infimum of all these errors is called the nth quantization error. So infimum of VR, P alpha, which is calculated by like this, and alpha is a subset of RD, and cardinal of alpha lies between 1 and n in the case of nth quantization error. We always assume rth moment, that is this quantity is finite. Then there is some set alpha for which the infimum occurs. That is, we can write this expression as minimum, because when alpha exists, then infimum becomes minimum. And infimum minimum becomes same at that time, of course, as you can see in any analysis book. Such set alpha for which infimum exists is called an optimal set of n means for P. Now, what is quantization dimension? Also, you understood that when you are representing by the number of points, suppose you have a large set of values, and you're representing by suppose a small number of points, and of course, if you increase the number of points, then the error, this quantization error will decrease. So this is the error curve, and this is the number of points. As the number of points increases, the error decreases. Here also error decreases. So what is quantization dimension? Quantization dimension gives you the speed, how fast the error is decreasing. Here error is decreasing slowly. So this is the expression for quantization dimension of order R. R log n minus log V and Rp. If it exists, it's called the quantization dimension of order R of the probability measure P. Quantization dimension gives the speed, how fast the quantization error goes to 0 as n approaches to infinity. So in this case, the quantization dimension is smaller than the quantization dimension in this case. So smaller means the error decreases quickly. That's quicker than the decreasing rate in this case. Okay, now next slide. Observation. The quantization error for any positive integer n depends on the metric and also on R. So if you look at this, here is the quantization error. See that this error depends on this R, the power R, and also on the metric, and R. But quantization dimension never depends on the metric. Does it depend on R? For an absolutely continuous probability measure, quantization dimension equals to the dimension of the underlying object. It does not depend on R. For example, the quantization dimension of uniform distributions defined on the line segments, circles, squares, or hexagons are equal to 1. And also, Euclidean dimensions of line segments, circles, squares, hexagons are all 1. For some details in this regard, how the quantity dimension is 1, one can see this paper written with Professor Rosenblatt from the University of Urbana-Champaign, and this paper is already published in this journal. Now, for a singular continuous probability measure, for example, for a probability measure supported by a fractal, the quantization dimension depends on R. So in absolutely continuous case, never depends on R, quantization dimension. But in the case of fractal probability measures, it depends on R. Because of that, it is highly interesting to investigate the quantization dimension of the probability measures supported by fractals. Now, what is quantization coefficient? For any S positive real number, the numbers limit infimum and limit supremum are called the S-dimensional lower and upper quantization coefficients for P of order R. It is known that if the lower quantization coefficient and upper quantization coefficient are finite and positive, then this is R over S, and R is that R that I told you before, is equal to the quantization dimension of P over R. The converse of the above statement is not true. For example, see the paper Shivam Dubey, M. K. Roy Choudhury, and Saurabh Verma, quantization dimension for a generalized inhomogeneous bilusive iterated function system. It is available in archive. It is just written. You will see many interesting results in this paper. Now, is there any connection of quantization dimension with other dimensions of dynamical systems? Yes. Remember here, if the quantization dimension does not exist, then we can define lower quantization dimension, which is limit infimum, and upper quantization dimension as limit supremum. When limit infimum and limit supremum are same, then we call it as quantization dimension. Lower quantization dimension always lies between Hausdorff dimension and lower box counting dimension of the measure. Upper quantization dimension lies between packing dimension and upper box counting dimension of the measure. So now, it is extremely difficult to calculate the optimal set of n means for a probability distribution, but you can easily calculate quantization dimension. See that here. It is not necessary to know optimal sets to calculate the quantization dimension. For example, let us take this discrete set, infinite discrete set, and the probability is defined like this way. 1 over 2j delta of 1 over j. So that means probability of 1 is half. Probability of the occurrence of 1 over 2 is 1 over 2 square. And the probability of 1 over 3 is 1 over 2 cube. And for 1 over 4 is 1 over 2 there 4. Take beta equal to this. Now, how to calculate the quantization dimension? Take beta equal to this, then we get the error squared Euclidean distance with respect to the squared Euclidean distance. This is the error formula. VB beta less than equal to this. And then V and P. So V and P, so this is beta contains n elements. So the error is this, less than equal to this. So V and P is a smallest error. So it must be less than equal to VP beta, which is less than equal to this number. And of course, this is non-negative number. Then you can calculate by squeeze theorem quantization dimension equal to 0. Because this goes to 0 and this is non-negative, quantization dimension is 0. So that is the quantization dimension of the measure P is 0. Now, do you know the optimal sets of n means for any n? Look at that here. Optimal sets of n means are known up to certain positive integer. For example, up to n equal to 301. But for large values of n, it is not known yet. So it is an open problem till now. And to know more details, you can look at this paper. R. Kavasag, Hag, Mendoza, and K. Roy Choudhury, Optimal Quantization for Discrete Distributions. This paper is also available in archive. And I'd like to stop here. Thank you very much for listening.